So I'm excited to present CAAFE today, our work to combine large language models and automated machine learning to automate more of the data science pipeline. Specifically, we worked on automated feature engineering in this work. So classical automated machine learning has been focused on automating the model building part of data science. So in this model building part, you make algorithmic choices, tune parameters, select models. All of these technical aspects of data science problems can be well automated by traditional automated machine learning. Now, using large language models, those are actually context dependent and they have a lot of real-world knowledge. So using them, we can actually automate more of the data science process. That is also parts of the data science process that are semantic and depend on the context of the data set. That means what is the real-world meaning of the features in the data set. And this is where CAAFE is focused on. In this work, we picked one of the use cases where this real-world knowledge comes in very handy, and that is in data engineering, feature engineering, which means changing the features of a table to get better results. So in feature engineering, to understand a bit more what the idea behind it is, we have an example here on the left-hand side. We have the orange dots and the blue dots here, and orange dots map to one class, blue dots to another class. And if we want to learn a classifier, make predictions here in this example on the green dot, it is not entirely clear what that mapping would be. Now, the idea behind feature engineering is that we can create new features or remove some features so that the mapping becomes more clear to a prediction algorithm. Classical feature engineering has not used semantic knowledge on what these features actually mean, also the base features, what they actually mean. So we want to change that because we have observed that oftentimes the feature meaning actually tells you a lot about how the features should be engineered. For example, if you knew that the features going in are actually weekdays or the days of the week, and then the classes are whether a person is working or has a day off. Now, if you map the days to either being weekdays or being weekends, it is quite clear what the solution to this problem becomes. So with semantic knowledge, it's much simpler to solve this problem. Now in CAAFE, the user first specifies the problem context and the dataset. This is then given to a large language model, which generates hypotheses for transforming the table by just generating Python code that does so. This code is then executed by an interpreter, and then the performance after this feature engineering, after executing that code, is validated on the dataset. And if the engineering was successful, if it improved performance, the features are kept or the changes are kept. And if it wasn't, they are discarded. And this is iterated over multiple times. So CAAFE can also build on previous engineering iterations. Now, in this example, we show how it works. Here on the top, we define a CAAFE classifier, we define the language model used for it and how many engineering iterations should be made. And then we fit it on a pandas data frame here. We specify what the target column is to be predicted, what the dataset description, the meaning of it is. And then when we let it run, we see here the dataset description is a spaceship Titanic dataset from Kaggle. And we see the features being generated here. The deck feature, for example, was generated. It's based on a cabin feature where we split the string into parts and we extract some of it. And we see this feature actually improved the predictive performance of the algorithm of it, so it's being kept. Next feature here didn't work, so it's discarded. Another feature here was useful, it's being kept. And the last iteration, it helped as well. So we see after a few engineering iterations, the performance improved quite a bit. And this was the performance in the end on the test set. So we see this also generalizes to the entire set. Another example here is on a tic-tac-toe data set, where it's described that the features are whether a player has put a mark on a certain field, and then CAAFE generates these features which actually test all the combinations that a player could win, if it's in a row or a diagonal or a column. And we see the first iteration helps quite a bit already. The second iteration gets the accuracy perfect in this example. Tic-tac-toe is a rule-based game, so here it is quite simple to solve the task at hand. So this really depends also on the dataset. It should be engineered and rule-based datasets. Domain knowledge helps a lot here. So when we evaluate this on a larger set of datasets, we find that the feature engineering with CAAFE helps in almost all of the cases that we evaluate. So please take a look at the paper for details on these datasets. They are quite small in terms of samples and in terms of features. They're small in terms of features because more features increase the length of the prompt, which becomes infeasible at a certain point. You have around 20 to 30 features. That error recovery works in all of the cases. So sometimes the code generated is just false, it doesn't work. Maybe a feature is hallucinated, and then we pass the error message back to the algorithm, and it can, in the next iteration, produce the correct code. So in conclusion, we think this is one step in automating more of the data science workflow. Now we can automate semantic knowledge into the workflow, and I think this can open up a lot of possibilities in automated machine learning. Our code is available on GitHub, and we also have a Python package, which is quite simple to use. However, caution is needed with this. First, we have automated code execution. We have a wide list of operations that are allowed in the code execution, but this can still be dangerous. So we are executing code generated by AI, and when we execute this on our system, there could be malicious users that maybe inside the data science context and can inject some commands, or the AI doing something we do not like, or just random events where maybe an infinite loop is called and the system could crash. So automated code execution is problematic. We try to solve it with a whitelist, but this is certainly not perfect. Also, job displacement is also a real fear. Whenever we automate more of any job, this is a possibility. Also, language models can replicate biases, and when we apply these language models now on data and make predictions on this can contain the same set of biases. So whenever data concerns real human beings, caution is really needed here. Thank you very much.